This was originally a talk that lasts about 45 minutes, and I'm going to try to cut it down to half an hour, which is something I'm really, really bad at, so this is going to be interesting. So for those who don't know me, my name is Michael Jennings. I work at Los Alamos National Laboratory. I'm the platforms team lead in HPC systems, which basically means I'm responsible for the people who run all the supercomputers. I would normally go through this and do a lot of introduction about LANL. We don't really have time for that. So the short version is we simulate making things go boom so that things don't actually go boom in real life. And that beautiful picture of the northern New Mexico mountains was taken from my backyard, and yes, I am hiring. So Los Alamos has a long history in high-performance computing. I wouldn't necessarily say we invented it, but we certainly helped. And as a brief aside, there are a lot of people here who are working in this space, and we are really looking for collaborators. So I promised the author of this that I would mention his project. We just released this on GitHub. We're looking to revolutionize how we provision our systems. All the stuff that we have been using to date is really old and outdated. A lot of it's written in Perl, which it's ironic for me to say this given the workshop that's going on upstairs, but I'm going to say it anyway. Perl was created for a world that no longer exists. And I love Perl to death. It's one of my favorite languages. We got to move on. So we've implemented this thing that we're calling Kraken, which is a distributed state engine. We're going to be trying to use it for provisioning, but also potentially other interesting things. So check it out, and hopefully you're willing to either help us with it or tell us that it really sucks and what to use instead. So first, a little bit of history. If you were here last year, hopefully you remember the talk I did on Charlie Cloud, which is our container runtime. I don't have time to repeat that talk, obviously, but if you weren't here, please do check it out. The URL is there on the bottom. It goes into a lot about containers in general, not just Charlie Cloud. So if you're not quite sure what containers are, how they work, what namespaces are, all that type of stuff, that's in there too. And I would be remiss if I didn't at least mention Charlie Cloud and NERSC Shifter are both R&D 100 finalists for this year, which is pretty awesome. And Charlie Cloud has been moved into the HPC project on GitHub if you're interested in contributing. And lots of new work has been done in the Charlie Cloud world since my last talk. We got students, and students are great for doing the stuff that nobody else wants to or has time to do. So they've been hard at work for the past year. Okay, so what the hell is up with the title of my talk? Also last year, there was an excellent talk given by a guy named Quinn, if you're familiar with his Last Week in AWS blog. He did a fantastic talk, and I'm going to, if you'll indulge me for just a little bit, play an excerpt from his talk because his talk kind of inspired mine. Oh, I should preface this first. At the bottom, this part of his talk, he recalled an incident like 5 years or so before, and I've tried my darndest to find who that speaker was. Can't find it, so if anybody knows, let me know. There was a fellow DOE speaker at one of these conferences who did a talk on golden images versus configuration management. It was his first talk at a conference. He was really, really nervous, gave what Corey said was a really good talk, And at the end of it, he asked for, are there any questions? Guy gets up, goes to the mic, and says, that's not how we do it at Google. So this is Corey's reaction. Yeah, so sound. I don't know where my headphone jack is. You know what? Never mind. Yeah, well, watch the talk. It actually is a really, really good talk, and it's worth your time. The short version is Google, what works for Google is great for Google. Other companies can't just say, okay, this is what Google's using, let's use that. Each company has to evaluate the pros and cons on their own as an individual entity. And Google is really good at shutting off things that people are using every day. So what makes high-performance computing so special? Why do I refer to it as another planet? Well, there's something about being here at a conference full of DevOps and SRE people that reminds me just how incredibly different we actually are. So why are we weird? Well, for one thing, we have a very different access model of how we run stuff. In the web app world, you can have developers having root, you can have operators having root, everybody gets root, no big deal, right? Well, in HPC, we're very, very careful about that, and especially at a place like Los Alamos, we have to be extra careful about that. We have very, very different constraints. We have different networks. We have different security levels, even sometimes on the same machine. So it's a much more complex and nuanced environment. We need bare metal. We can't run in VMs usually, or containers, traditional containers. They don't necessarily provide the level of performance that we're looking for. And we typically provision statelessly so that things like upgrades and migrating to new operating systems and changing things around, we simply reboot. The side benefit of that is if you've got two identical nodes that are running the same stateless image and they're behaving differently after a reboot, you know it's hardware, guaranteed. In the cloud world, there's only a few things that a typical node, a typical machine needs to be able to access. Processor, obviously, a little bit of memory, a network, possibly a software-defined network, and maybe a little bit of storage and possibly some local services like etcd, something along those lines. In the HPC world, we have lots and lots and lots of very specialized hardware and software that we have to provide performant, reliable access to, including some things you've probably never either heard of or worked with, things like InfiniBand, OmniPath. Obviously, we also use accelerators like GPUs and FPGAs. We have multiple levels of layered storage, all the way from a local TempFS and RAM to local scratch disk, burst buffer, which is essentially a high-speed, nearby distributed file system layer. We have parallel storage like Lustre or GPFS, all the way down to tape eventually. And we have to provide access to all of those things seamlessly. And of course, there's a scheduler or resource manager thrown in the mix somewhere that has to be able to monitor and manage whatever job is running on each node. What security threats do we face? Well, typically, if you're talking about web apps, it's things that are bugs, like SQL injections. Well, nobody uses SQL anymore, right? Bugs in the web app that somebody can exploit to potentially gain access to the underlying virtual machine or services. In HPC, we've got everything from credential theft to actual nation-state actors persistently trying to break into our systems through any means they can find. We also have non-security threats, things that a normal user can cause to go wrong on a system, not because they're malicious, but because they don't know any better. The classic example being walking a file system. Normally doing a find slash, it's going to take a while, but you don't really think much of it. But crawling a parallel file systems are notoriously difficult to parallelize and distribute in a performant way, particularly when it comes to metadata. We're not very good yet at distributing metadata. And so if you do a file system crawl, you're going to pound the crap out of the metadata server. We also care a whole lot about something called Jitter, which a lot of people in cloud space have never even heard of or cared about. Jitter is all of those other things going on the node apart from the job that you're trying to run. Each and every one of those can cause delays in processing, which if you're doing a MapReduce algorithm, you probably don't care too much about. But in tightly coupled applications, it really, really matters. Those of us in HPC actually kind of started chuckling when the MapReduce paper from Google came out, not because there was anything wrong with it, but seeing how MapReduce has really changed the world fundamentally kind of caught us by surprise, because doing things this way is something that we in HPC had termed embarrassingly parallel for a long time, because it wasn't the hard problem that we were trying to solve. This is my attempt at trying to draw something in PowerPoint, but it's basically your traditional MapReduce type of workflow. Divide and conquer. You split your data up into little bitty chunks, and then you merge your results back together at the end. When you've got a task like a search engine, you can have one machine searching 3 billion web pages, or you can have 3 billion machines each searching one. The end result is the same. Contrast that with something like adaptive mesh refinement, which is one of our bread and butter algorithms at Los Alamos. Adaptive mesh refinement simply means we take a 2D or a 3D grid of reality, whether that's Antarctic land ice or subatomic particles. We split reality into squares or cubes of varying sizes. That's the adaptive part. And each one of those grid cubes or grid squares is a job. And then that job has to communicate with all of the jobs around it. So you can see all the little different grid squares there on this map of the Antarctic land ice. I picked this because it was available on Google and verified unclassified information, but you can kind of extrapolate how you can use the same type of technique for other interesting problems that we care about. So when people at Google and Facebook and Amazon say at scale, usually with their noses about like this, they mean something very different. They're talking about millions and millions of machines that are really just endpoints to them. They don't really care about them. They're throwaway. When we talk about at scale, we're talking about hundreds or thousands up to, our largest machine is about 20,000 nodes. And for large problem sizes, each and every one of those nodes has to be able to communicate with literally every single other node on the system quickly. So when we say at scale, it's a very different type of problem. So once upon a time, when containers were still new and Solomon Hykes still worked at Docker, we in HPC eventually actually, yes, learned that Docker existed and that it could do interesting things. And we tried to convince him that he should care about the things that we cared about. We failed. So Docker doesn't really address many of our use cases, many of our unique problems, because those problems don't exist in the cloud space. So, as I talked about last year in my Charlie Cloud talk, we had to kind of create our own, at least for the time being. So these are the most prominent container runtime solutions in high-performance computing. We have Charlie Cloud, which is the Los Alamos project. We also have Shifter, which was created by the NERSC folks at Berkeley Lab. And then there's Singularity, which is maintained by a company called Scilabs. So I won't go and read this to you, but basically it lays out the differences between the various solutions. For Charlie Cloud, we chose to base our runtime on user namespaces, which allows us to provide a completely unprivileged binary that users can install themselves, rather than the system administrator having to install something that's setuid root or that runs with added privilege. Shifter went in the other direction. They chose to do the setuid model, but went to great lengths to ensure that they did it in as safe a manner as possible. One thing that they did was create an image gateway so that the image gateway downloads the repository from Docker Hub or whatever registry server and translates that into Shifter's format independent of the user. That way there's no chance for a malicious user to present a corrupted file system image to the container runtime. With Charlie Cloud, that's not an issue because thanks to user namespaces, the runtime actually executes without privilege as the user who's running it. It does require, of course, a kernel that's capable of providing unprivileged user namespaces, which is going to be the new default in RHEL 7.6, I believe, and is currently available on SLUS 12 SP2 and greater. So I put it on there because it's one of the HPC focused runtimes, but I'm gonna kind of blank out that column over there, and here's why. I know way too much about Singularity 1 and 2 and how they were written and the risks involved, and I can't in good conscience recommend that anyone actually run it. I know absolutely nothing about Singularity 3, the new release, in which they've completely rewritten it from the ground up again, this time in Go. And I don't know anything about that at all. Don't know how it was written, how it was architected. So I can't say anything intelligent about the new code at all. So what about the other possible solutions that are out there? One thing about both the Charlie Cloud and the Shifter projects, and I talked to both, neither camp is particularly married to their project. Really, both were created because there wasn't a solution that fit that particular need at the time. If sometime down the road, whether it's a year or 5 years or whatever, if there's something else that has broader support, something that comes out of OCI or Kubernetes or whatever it happens to be, if there's something that does a better job of fulfilling the needs of the users, we're going to move in that direction. What we're using today fulfills a need, and that's where it ends. And we're actually really hopeful that at least one of these options, or possibly the cryo stuff that Red Hat and their community is doing, will be able to fulfill what we need. So the Open Container Initiative, for anybody who's not familiar, was created essentially to settle an argument between Docker and CoreOS/Rocket. Ultimately, both because of the security features added to the container format and the coalescing of a community around a shared standard, both have been really, really good for containers and Linux in general. Rootless Run C is a project that's being done by Alexis Sarai out of SUSE. Looks really, really promising, and he has some very astute analysis of the other options that are out there. He didn't really have a logo on his website, but what he said about Singularity made me chuckle, so I used that instead. Docker Inc. There's a guy named Christian at Docker who has been going to lots of the HPC shows and talking to all of us about our needs and how we can work together to help fulfill those. So we're hoping that some development can happen there. I mainly included this slide because of that graphic. If you've never been to l.cncf.io to look at the cloud native landscape, you're missing out, because holy crap. This is why keeping up with container and cloud technology is such a nightmare. There's so much of it. There's so many choices for any one role. Somebody had to come up with a way to organize that information and make it digestible to those of us who are in the trenches every day trying to make this stuff work. So I strongly recommend going to that website and checking it out. Lots and lots of useful information, or just show your boss that graphic, because holy cow. So the ECP project is the Exascale Computing Project, and there's a container working group that is trying to organize and coalesce a number of different things. One of them is a paper around what's the current state of the art in HPC containers, and some more documentation, best practices, that type of thing. Charlie Cloud and Shifter are both working on additional features for usability and kind of trading off what each one is good at. Shifter is really, really good at user experience. The user says, give me this container, now run my job in that container, thank you very much, done. All of the work is on the part of the sysadmin. Contrast that with Charlie Cloud, where literally the admin has to do nothing whatsoever. It's all on the user side. So we're working together and separately to try to to coalesce around improving both projects. If there are any questions, I'm happy to take them. If you can come up to one of the mics or the mic, that would be great.
You mentioned the burst buffer in one of your slides.
Mm-hmm.
Can you just provide a little more detail about that?
Sure. So one of the challenges of running jobs at scale is checkpointing. As you know, systems will inevitably fail, and the more nodes you have in your job, the more likely it is that they're going to fail at some point before you get to job completion. So what our division leader, Gary Greider, realized was that we needed a layer of storage that was closer and faster than anything we had available. So he designed what we call the burst buffer, which are they're essentially compute nodes that are near the cluster that have very, very fast SSDs. And there's a system that provisions storage across one or more of these SSD-bearing nodes. And we can do very high-speed transfers of data from the compute nodes on, in this case, Trinity, to the data warp burst buffer nodes that are supplied by the vendor, Cray. And so we can checkpoint very, very large jobs very quickly using that distributed burst buffer.
You mentioned the needs of the HPC and its specific bare metal requirements and its high performance built into its name. You spoke about Charlie Cloud as a way, as a container. I guess I don't want to misspeak here because I know there's a lot of details around like is it the manager, is it running it, but I don't want to. I guess the question is, what about, I guess, the Charlie Cloud architecture and lets you get access to maybe more of the horsepower of the raw material of your computers? Is it made differentiate from other cloud management tools or container management tools?
So the big thing is the lack of virtualization and the lack of unnecessary abstraction. So if you run in a VMware instance, then by default you are insulated from the actual hardware. You're not running on a real CPU per se, you're not running on real RAM per se. There's a level of indirection that happens there. With containers, if you're running inside a Docker container, by default you get a network namespace in which you have a virtual network device that has to forward through a MAC VLAN pipe essentially to the rest of the world. There's a level of abstraction there. You also don't get access to probably the most important resource, which is InfiniBand or OmniPath or the Aries high-speed network. Having direct access to that is arguably the most important aspect of running jobs in HPC. And so the HPC container runtimes are specifically designed and coded to enable you to access the high-speed network, the parallel storage, things like that. Whereas stuff like Docker, there's no Docker graph storage driver for Lustre or GPFS, though I have asked for it. So we'll see.
Is this like in the VM world, there's like the PCI pass-through type stuff. Is it the same kind of concept where the device driver lives within the container, or am I just needing to get more educated on Charlie Cloud?
It's somewhat analogous, except that it's not happening at the kernel level. There are actually libraries, MPI libraries that exist on the host. And one of the new developments is being able to actually insert in a just-in-time way and do some manipulation with the SO names to provide those libraries into the containers so they can be used as if you were running on the host, but inside the container.
Thank you.
Thank you.